instructors like me who were teaching things to those investigators. We weren't passing on the information that they needed to get the job done. So where did the fire start? It was right up in this quadrant in the trash can. We did another fire in the back room. As I said, took 3 minutes. 3.5 minutes to flash over, 3.5 minutes post flashover. But we put the fire at the end of the bed down here. We had the exact same pattern, or virtually the same pattern on the back wall, which went to show us at the time that it didn't matter where the origin was. What mattered was when we got into the post flashover burning period, we would get the same effects solely by ventilation. So what was creating the pattern was this doorway, not the origin of the fire. On this particular fire, the fire starts here in the trash can, and look at the pattern. There is a pattern there, right off of the trash can. It's a V pattern, almost. You can see it right here, coming right off of that. But it's not as big a pattern. It's not the most severe burn like we had on the back wall. Sure, please. Right. They sure are. Yeah. I don't know for sure, but that's part of the. Oh, okay, sorry. The question was, I mentioned two terms when I was talking about the reading from the origin matrix analysis. And I think the second block down was flashover. The third block down was short-term burning in post-flashover and long-term. I don't know for sure what the short-term versus long-term is. Perhaps it goes into it in 921. I would say if you hit flashover and then burn for a minute, that's short-term. If you're up into the 3 minutes and beyond, you're into the long-term. Now, how do you do in the middle? I don't know. You might be having to kind of interpolate between those two diagrams, between the third row down and the fourth row down. Yeah, if you didn't hear that, he said because of the modern day fuels and the fact that flashover often happens fairly quickly, firefighters may not even know about the fire until the thing has gone into flashover. So the chances of extending a fire into that long-term burning post-flashover are pretty high. Yeah, you're right. Majority of people, if I could get this thing to work, I would show you. They put it right into this quadrant here. And the reason they put it into that quadrant, oh, I keep forgetting. Where do most of the people put it? Right here, in this section right here. The reason they did was because of that. See that stack right there? That damn stack caused that pattern. Okay. This is a joke. It's gotta be. No, it's because of this pattern here. Low level pattern extended underneath the table. And again, we didn't ask him to go in and do a full investigation. What we said was, please go in, tell us where you think it started based on what you see. So what did investigators do? They went in and said, look at the size of that pattern. It's massive. What people used to think, and I think were probably taught along the way, was think of it this way. The fire at the origin burns for the longest amount of time. Therefore, it should create the most amount of damage. Well, that has an inherent assumption built into it, which is that the level of burning is equal throughout. The reality is that's not the case at all. The level of burning in one area may be very high early in the fire and then go to zero. The level of burning in another area may be virtually nothing at the beginning, but then go to the races. And that's what we see. So using that logic, they see this big pattern and came up with the idea that, well, that had to be where the origin was. I've talked about a few times with people in the idea of aviation, when people design aircraft, they have two general paradigms that they follow. The subsonic aircraft, the ones that never go faster than the speed of sound, and then the supersonic aircraft. If you design all aircraft using just one of those areas of physics, you're going to get half your aircraft that don't function very well in the other regime. Same thing goes with fire investigation. We have two kind of regimes that we deal with a lot. Ventilation limited or post-flash overburning, fuel limited or pre-flash overburning. If you apply the wrong rule to the wrong regime, chances are you're going to make a mistake, at least with regards to the origin. We'll talk about why that is. Okay. I know we said we were going to take a break at 2 hours, but I'm going to take 5 minutes break right now, say really bad words, and I'll be right back if we can just put that on hold. I'm gonna have to what? Might as well. Yeah, this was pushing back. Okay, sorry about that. A little bit of hardware issues, I guess, or maybe the software issues between my ears. I'm not quite sure. I apologize. It probably is operator error. All right. So we're going to try to get through this a little more smoothly. And at the break, we will break at about 3:15, 3:20, something like that. At that time, if nothing else happens, I'll change the other computer out or something. So that's what happened in 2005, the demo that I just talked about. We had the 53 students that came through. The purpose of the demo that we gave them was almost set up in order to, I don't want to say make them fail, but it was set up in order to allow students to recognize what they might not realize in terms of fire behavior. We had done similar tests or similar burns down at the Federal Law Enforcement Training Center for 15 years previous to that. And in every case, we did it at the very start of the class to try to shock students into recognizing maybe there's something you can really pick up from this training. That was our purpose there. Now, that being said, a few years later in 2008, the folks for the IAAI had given us an opportunity to take this same material and try to generate some good fire testing that could be used for CFItrainer.net. And if you've ever been on CFItrainer.net and looked at the post flashover module, what you'll be seeing is what's coming off of these photos here. We took the same basic layout for the compartments, and our purpose there was to set 3 fires. We were going to set all 3 of them the exact same way, and the only difference was going to be the length of time that they burned post flashover. So with your question a little while ago, what's the difference between short-term post flashover, long-term? We were going to try to show that as to where does this stuff really take off. The idea was to stop the first fire at about the time it appeared flashover had occurred. The next fire was going to go 2 minutes post flashover, and the third was going to go 4 minutes post flashover. This is the ATF Fire Research Laboratory and the forensic facility back in Maryland. See a firewall that goes across the building about right here. That separates the fire lab, which is to the left, top left, away from the rest of the forensics lab. Down here, everything from ballistics to chemistry lab to fingerprints and all that sort of thing. The 3 cells, much like the ones in Vegas, were constructed at 12 feet by 14 feet. They each had doorways here in them. This particular cell is the first one that was going to be allowed to burn until the time of flashover, and at that point, we were going to extinguish it. All 3 of these are inside. If you haven't heard about the lab back there, see these straight lines here? Those are the boundaries of a big hood system that collects all these hot gases. Going back to that last photograph, when all the hot gases are collected, you go back, Jeff? There it is. Back here in this section back here is a pollution control facility. So all those hot gases get collected in here. They're pumped through this system, and all the pollutants are pulled out there. So outside the building, you won't even know whether there's a fire going on or not. So this fire was burning. All the hot gases were going up being pulled up into the fan, and we allowed the the compartment to burn, and we gathered all sorts of data that we never gathered in Las Vegas. Yeah, what happens in Vegas stayed in Vegas, all right. It really raised a lot of eyebrows and a lot of arguments as to what the cause of that test was or demo was. This was cell number 3. You can see that's in full-on post-flashover burning. We allowed that one. It actually started out to be 4 minutes post-flashover. We stopped it at 2 because of some other problems we had with the second cell. But that didn't really matter because it ended up helping us out, and I'll show you here in a minute why. Layout, very similar to Vegas. We've got a dresser down here. Instead of a nightstand on this side, we put a chest of drawers, nightstand here, table light over here, I think. One of the things that the ATF Fire Lab does is hire contractors to build these things. Well, these guys decided to do it up real fancy, and not only did they put a doorway in, they put doors. The door was what kind of caused us a little bit of trouble. And back in this corner, we have an upholstered chair this time versus a wicker chair that we used in Las Vegas. The reason we used upholstered chairs is that we realized the new beds that we used, brand new beds at the ATF Fire Research Lab, were from the batches of beds that were hit with all kinds of fire retardants and would not grow large enough in order to put that room into flashover. So we added some extra fuel back here. Again, 14 feet by 12 feet. The doorway's in the same position. Inside the room, all the furniture was brand new, kind of set up almost like a little college dorm if you wanted. All 3 cells were the same. The only difference in any of the cells was that the color of this chair was brown in one cell, gold in the other 2, just because we didn't have enough of the supply available at the furniture store. These cords are thermocouple trees meant to measure temperature. We have cameras, heat flux gauges. Oh, this is a sprinkler system. We would pull the gases out of the room and measure them for oxygen concentration, CO2, that sort of thing. There's more gas ports there. At the other end of the room, more cameras on the floor. We did have electricity to the room, CO and smoke detectors up on top. So this thing was set to gather all sorts of data for us in our testing. Fire 1. After this fire burned, this is the one that we saw up here first. This is the one that went to flashover. This is what was left. We have a clean burn area right by the bed, and I'll tell you right now, the fires started just like they did in Vegas at the top of the bed in a trash can of paper. We see some clean burn there. The back of the chair is burned away. Carpet is burned away except underneath the bed. Looking through the doorway at the back of the wall, we start to see a pattern develop over the nightstand and the ceiling. This area to the right is actually unburned area right here. And again, this was stopped right at the point of flashover. At the top of the bed, we're starting to get a little bit of damage over by where the origin was, near where the clean burn was. Start to see some degradation of the mattress in that area. And pulling back a little bit, once again, the pattern above the nightstand and at the ceiling. And there's the back wall one more time. Okay. Into the room, we've got burned down to just about a foot off the floor. This is probably as the cool air was flowing through, the bottom was knocking away some of the hot gases that would have otherwise burned like this. And the carpet in some of these hidden areas wasn't burned too badly. And the camera down there survived just fine throughout that fire. Fire number 3. Now, I'm not going to get into these in great detail, but suffice it to say, fire 3 burned for 2 minutes post flashover. This was the one that was going to be 4 minutes, but because we had problems with number 2, we left it it was supposed to be 4 minutes. We left it at 2 minutes because of fire number 2 having problems. Notice this fire, which burned 2 minutes post flashover. We don't have a pattern here on the wall, even though that's where the fire started. We have more extensive damage on the head of the bed. Look across from the door, we see this pattern back here, kind of like the pattern we saw in Las Vegas, not quite the same. Of course, we had a little bit different furnishings. We did not have a big round table in this case. We just had a mirror back there, so airflow would have been changed. Inside the door, we had this clean burn pattern right next to the dresser, in between the door frame and the dresser. And kind of looking back from a distance, we're looking like this, at that big pattern on the wall, pattern on the ceiling. Everything seems to look like if you were to apply the things you might use in an early fire in terms of V patterns and stuff, that the fire may have started right here. Can we go back one, Jeff? One more, or until we can see that pattern. No, one more, where we see the whole back wall. That one. Okay, so we have this pattern here. Now, a lot of people, I would dare say, would look at that pattern and they'd go into a room, and if they were looking at this based solely on the kinds of lessons they learned for pre-flashover burning, they would say that is a V pattern which points down to the location of the fire. Now, Andy came up, and I didn't speak very clearly in the last section of the last class with my frustration on this little doohickey here. But what I said was, I started off by saying ventilation limited burning is post-flashover burning, and that is true. But let's start earlier. Pre-flashover burning, from the time of the fire onward, we're in what's called fuel limited burning. This is a term that you need to be familiar with if you want to do this in long-term profession, as a long-term professional. Fuel limited burning means that the size of the fire is limited only by the amount of fuel that you can get involved in the fire. So the more fuel that starts to burn, the bigger the fire gets. At some point, oftentimes kind of associated with the onset of flashover, you will transition. And now you're in a situation where no matter how much fuel you get burned to burn at the time, the fire doesn't get any bigger because it is limited by the amount of ventilation that can support that fire. In this case, it'll be limited by the amount of air that can flow through that door. It's just not going to get any bigger because you can't get any more air into there. So when we learn about these limits of ventilation limits or fuel limits or whatnot, that tells us what set of rules we need to apply towards investigating the origin in that fire. Now, in this case, I can tell you that once you get to flashover, you can pretty much take to the bank that you're in a ventilation limited condition. If we were to look at a pattern like this, we need to approach it with the idea of ventilation limited burning, which we'll talk about some more here. All right. And if we use fuel limited burning in our rules that we're going to try to decipher this with, we'd say this is a V pattern pointing to the fuel on the floor where the fire started. But that's not what happened. The fire started back in this other corner, as I pointed out. How did this V pattern occur? Very unusually, and if I hadn't seen it with my own eyes, I would have been skeptical. This fire burned from the top down. So get that right. It starts out at the top of the room, starts charring or clean burning the wall, and then as it burns down because of the way the air flows, we end up with this point. Oh, well, that's just a once in a million kind of test. No, because cell number 2, we had the same pattern. And I don't have all the slides in this presentation, but both cells had this same kind of thing. Both of them we observed on camera to start over here, directly above this table, and then move this direction as the fire spread off to the right, and then move on down. You're standing in the doorway. No, I'm sorry. The question was, am I saying this is fuel limited? No, fuel limited is up to the point of flashover, meaning that the fire is dependent solely on the amount of fuel that can get burning. Once you get to flashover, you go ventilation limited, because then the size of the fire is dependent on the ventilation. If I punched another big hole here, like another doorway, the fire would get even bigger, because now we're supplying it with more oxygen. This little section right here occurred when oxygen flowing through the door, or air flowing through the bottom of the door, hit that door and started to spin. It started to go into like a little tornado. It moved in between the door and the dresser and just sat there and burned and created that burning. Now, how do we know that happened? Well, in the second test, because the door closed on its own, much to our surprise, we put a block in that door, and that block interrupted that flow, and that pattern did not exist in cell number 2, even though everything else was the same. The back pattern on the wall did exist, but this one did not. It's all dependent on how that air is flowing in at the bottom of the room. Okay. Yes. Yeah. The question was, in the mini tornado area inside the door, is it like there had been deposits of soot there, but they were burned off? And yes, that is exactly what happened. There were deposits because of just the normal onset of flashover, but now we have a very oxygen-rich area that is able to create very efficient combustion and then burn that soot off as a fuel. Now, you bring up a very good point. We're going to go back into one of the first pictures, Jeff, where we see the back wall, or up the head of the bed, right there. This area right here, remember on the first test that we burned till flashover, there was a clean burn pattern there, right? You might wonder, well, why is there no clean burn pattern here? When this fire started off, up to the point of flashover, there was enough oxygen in this part of the room to be able to support that fire just fine. And it burned up and it created damage to the wall. When we went through afterwards and did some depth of calcination measurements here, there was damage, just as if we had a clean burn. But later, as the fire progresses and the available oxygen is consumed as it goes through the door on the way to that back wall, yeah, as the oxygen is going through here, it's being consumed before it can reach this back corner. So essentially, at the late part of this fire, this area back here is very fuel rich, and I think I'm possessed. What the hell? Now my phone's talking to me. Anyway, the oxygen's consumed before it can get back there. So what happens back here is that later on in the fire, we're getting a lot of soot being released off of this chair, and it redeposits on the wall over a damaged area of sheetrock. Very interesting. So, any other questions on that, Andy? I know I forgot you there. Excellent question. He said he wants to know, how does this correlate with fire movement and intensity? There is not a simple answer, in my opinion, as to how that all is going to work. The next example that we're going to give here from 3 to 4 or 4 to 5, I'm going to go through a case example, how movement patterns were interpreted that weren't movement patterns. And as a result, threw off the entire investigation. One of the things in 921, they talk about movement patterns and intensity patterns. They're the two basic patterns that we rely on to create essentially class alpha materials to burn, all right? Anything that chars and so on, paper, wood, even some of the thermoplastics. You've either got a movement pattern or you got an intensity pattern. It's up to us to figure out which is which, and it's not always clear. When we go back and we're doing our hypothesis development and hypothesis testing, one of the things I hope that you will be able to pick up from today's presentation is that during the hypothesis testing phase, it is important for you to try to figure out how air flows. I'll show you some ways that you can do some testing to try to figure that out, to give you some of those answers, but it's not necessarily an easy predicament that you're up against. Sometimes it's very difficult, but we'll talk about some of the techniques that you might be able to use. You know, some people have the Midas touch. Today, that's not me. Okay, here we go. Home. Just kidding. Okay, all right. So again, I apologize with this, that we'll get through it. Okay, so we're going to go ahead and move ahead past the slides that we've seen here, past that doorway. And there we go. So where the fire started. In this case, I've already told you, these fires were started in the exact same place, up at the head of the bed. They're up in that trash can, just like the fires in Las Vegas were. The point was not to try to throw too many variables in here. It was try to do things the exact same way and see how the change of one variable, which was time, would affect this. Your question earlier about long-term burning post-flashover versus short, you can see how the difference just 2 minutes will do. If you have a room the size of a basketball stadium or a big warehouse, maybe 2 minutes might not be much of anything. Maybe then you're going to have to go 5 minutes or 10 minutes or something to really be able to notice a difference. I don't know. It's kind of a case-by-case basis right now. I don't think there's a simple answer for that. You're right. And in case you didn't hear that, or if the folks on the Zoom feed didn't hear that, what he said was that this kind of reminds him of how when people used to examine spark plugs on cars, they'd pull them out, look at the patterns to find out whether the engine was burning too rich, too lean, whatever. And a lot of that determination was based on the amount of soot deposition they would see. And you're right. It's basically just combustion. We just happen to have it in a room here. So the fire started again in the trash can, and the studies were all based upon trying to figure out the effects of time. But just like in Vegas, these were all set well apart from the most prominent burn patterns. And that goes back to the statement that was made earlier in which 2017 version of 921 specifically addressed, which said your area of most severe damage is not always your area of origin. And in these cases, that's most definitely the case. I would say as a general rule, once you get to flashover, once you get to a ventilation limited state, you got to be really careful in trying to associate the areas of most damage with your origin. Because at that point, that's when things change. You you shift from the fuel limited regime to the ventilation limited regime. And the rules, for one, don't necessarily apply to the other set of situations there. This quote came out of another court case that happened. And I believe, I'm not sure who said this. It might have been John Lentini. I don't know, but I think it's correct. Can everybody read that? I'll read it. It says, the fact of the matter is that when investigators use visual cues from burn patterns alone to estimate the areas of origin of fully involved fires or flashover type fires, they will very likely make mistakes unless they really understand and account for the changes in fire pattern generation that occur as fires progress into and beyond full room involvement. That's a long sentence, but essentially it's saying what we've been talking about. If you use the rules for fuel limited burning to try to find the origin in a fully involved compartment that's gone into a ventilation limited burning, you're likely going to make mistakes. This document here, has anybody seen this document here in the room before? This is available online. I would highly recommend that if you have not seen this, and most of you haven't at least, that you try to find this and take a look at it. It talks in great detail about these very principles related to ventilation, how ventilation affected fires can be misinterpreted, and what happens in court cases where that occurs. What's happened in the past, what are the resources to be able to learn from to avoid that in your own cases. So it's called Forensic Science Assessments, Quality and Gap Analysis. Now this covers all sorts of areas of forensic science, DNA, ballistics, whatever. This particular one is on fire investigation. And I'm going to leave this next slide up here for just a second, but that is either put in the title of that document, or that's the webpage address if you want to do it. So if you want to take a picture of that or whatever, this is a document, like I say, worth having in your toolbox there. And as you probably know, there were no carriage returns here or whatever. This word is as default, and then it goes straight on into investigation.pdf. Anybody need that up anymore? Well worth having. If you're going to testify in fires, I would definitely download that, take a look at it, and see what you can glean from it. So now what do we do with all this? Well, we know there's problems. We know there's problems for investigators that have not been taught how to differentiate between fuel limited and ventilation limited. We know there's problems when people go in and take a look at a pattern and basically say one size fits all. More serious damage means that this burned for a longer period of time, yada, yada, yada. How do we get past it? We got to go back to the basics of fire dynamics. So we're just going to talk today about fire dynamics associated with ventilation limited burning. I think everybody that studies fire investigation and fire science starts off with fire dynamics of fuel limited burning. It's pretty simple. It's what we taught years and years ago and where we always start with. Starts off with the fire triangle. I know this seems simple, but I will tell you this is the single principle of fire behavior that seems to trip people up because it is so simple. They think, okay, we've got a fire in here. It's a big pattern over on the wall. How many people regularly walk into a fire compartment, see a pattern, and the first question that comes to mind is, I wonder where the oxygen came from? Hardly anybody. What do we all say? What fuel was there? Right? We're talking about all the time, what fuel causes this pattern? What fuel did this? Well, in a fire that goes to flashover, you have fuel everywhere in the compartment. It's not just located at a particular area. It's being emitted off of every fire or every fuel surface in there. that can be pyrolyzed, and then it moves around in the air currents. Where it burns is often dependent on where the oxygen comes from. The reason we got the big burn patterns on the back walls in Vegas and at the ATF lab was because that's where the oxygen was. It's not because that's where the fuel was. The fuel was everywhere in the room because everything had emitted fuel, it swirled around. So fuel wasn't the question. The question was, where's the oxygen? If you are faced with fully involved fires that have gone to flashover, and as you mentioned a few minutes ago, with a few minutes that it takes for a room to get to flashover nowadays, very unusual for a fire department to be on scene before that thing does reach flashover. If it's going to, then this becomes very important to you. In the world of basic chemistry and combustion reactions, we want to break down fire into this reaction right here, this formula. A fuel plus an oxidizer in the presence of energy, heat energy, will create combustion products. And here's some of the kinds of elements or compounds that work as fuels and as oxidizers, and the kind of products we'll get as combustion products. It's not all that crucial to understand what each one of these is, but the basic reaction here is important. Fuel plus oxidizer equals combustion products. If you've had my classes before, you've probably seen these diagrams. I try to simplify the chemistry of fire using these. For simple purposes, the blue, what I sometimes call ping pong balls up here, represent oxygen atoms. So since oxygen exists as O2, this is an oxygen molecule. This is a fuel molecule. I don't know what it is. Carbon, polyurethane, wood, whatever it is, it's all balled up into this nice little ball. But let's just call it carbon for right now. In these diagrams, the carbon is down here at the bottom of our screen. It's either in solid form or perhaps in liquid form, but it's pretty much capped down here. It's not floating around the room like methane or propane might be doing if we have a gas leak. It's all down here. And when we start off, we're at a certain temperature that does not allow that fuel to just suddenly break free of whatever matrix it's in and start floating around. But if we apply heat to it, we will start to break free some of these atoms or molecules, and they're going to start moving around. We often talk about temperature and heat as interchangeable. They're not. Temperature, an easy way to think of temperature is like a speedometer reading. All right, a speedometer, it measures how fast you're going. With temperature, temperature measures how fast molecules are flying around towards each other if they're in the gaseous state. Or if they're solid, how fast they vibrate. The higher the temperature, the faster they go. So we apply heat to raise that temperature. So the heat energy that comes into the system will start to break this stuff free and make it travel. The more heat we put in, the higher temperature we get, the faster it travels. Well, if this stuff gets going fast enough, we will start to get collisions, just based on the probability of how many other atoms are in there, or molecules. And one of these red ones will pop into the blue ones, and we'll eventually get to the point of combustion products. In this case, this would be something like CO2. Different ones here. This would be CO. It can still hit into another oxygen molecule and strip off an oxygen atom, giving you CO2, and so on. Now, every time we get a collision of a fuel and an oxidizer, and it moves into this kind of form, energy is released. That energy that is released can, in turn, break free more fuel molecules, get them flying around, and get them to go faster. That causes our fire reaction, as we call it, to progress. And as soon as we either run out of fuel or run out of oxygen or slow the system down because we're not releasing enough energy, then our fire starts to die off. This molecule here, a couple of fuel atoms, we can combine that with a couple of oxygen atoms, and when we do, we'll break these bonds, and then we'll create something like this. Every time we do that, the energy that's initially held up in these bonds will be higher than the energy in this bonds. What happens is we have a release. A release usually in the form of heat, sometimes in the form of light. Now, in fire, two of our common combustion products are CO2 and water. Every time we form CO2 or water from hydrocarbons, from oxygen, things like that, we will release energy into our environment. And when we release that energy and where we release that energy will control where the damage occurs. So just because you have a fire in a room, if I have a big fire on the stage, there's no reason to believe that the actual chemical combustion that's taking place up here is going to create damage back in that corner or in that corner or somewhere else. We would expect the damage from this burning to take place, that takes place up here, to occur right here. Just common sense. All right, and this is important, and we'll talk about it, why that affects our fire scenes in a minute. Now, in this case, we're looking at a picture where we've got an awful lot of combustion having occurred. There's a lot of CO2, there's less oxygen, and there's still plenty of fuel here. If this fire was to continue on and we'd continue to release fuel, because the number of oxygen molecules available has dropped down, the probability of collisions has dropped down, and our fire is going to start to die off. Probably thinking, well, how does that affect our fire scenes? Well, I'll try to show you here. In a diffusion flame, which is the common flame that we deal with in a fire, the way the oxygen and fuel reacts is pretty much similar to a candle. All right? Very simple. If you haven't seen the studies or the demonstrations on how a candle behaves, you can get on cfitrainer.net. There's a very good program there that talks about it. Just another photo there. Now, Jeff, can you move the cursor to the bottom left? You'll see a play on the screen there. There. Okay. All right. We'll fix this and I'll show it to you later. But get it? Okay, we'll show you these videos after the break. It kind of shows one of the points. I'll go ahead and I'll come back and do it after the break. When we look at a flame, we can actually look inside that flame if we take a metal screen and we put it down over the top. When we do, we see this ring-like structure. As we lift that metal up, the ring closes. As we drop it back down, it opens back up again. What we're seeing there is the equivalent of this. We've got what I'm calling the light zone on the exterior. On the inside here, we have fuel gas. And what you can't see, but what exists is the flame zone or the reaction zone, where that red circle is. That particular zone is where the heat is released. That's where the carbon is meeting up with the oxygen. It's reacting, the bonds are breaking and reforming, and that's where our energy is released. If we were to measure the temperature in this particular flame, and we took a thermocouple probe from the outside, we'd start to see a temperature rise here, maybe on the order of 900 or 1,000 degrees. It get higher and higher and higher, 11, 12, 13 at the red line. We might be 15, 1600 degrees Fahrenheit. And as we go through that line into where the fuel gas is, it would drop way back down, maybe 500, 400, something like that. The reason is inside this area, there is no chemical reaction going on. There's no chemical reaction going on because there's no oxygen that is getting into the reaction zone. The oxygen comes in from the outside. And it diffuses towards the fuel gas, and where it meets, that's where the reaction occurs. Because that's where the reaction occurs, that's where the damage occurs. This will show up in a compartment, and we'll go through that. Now, I know we're getting real close to the time for the break, and frankly, I think I could use one. I don't know about anybody else. So how much time you want to take, Jim? 15 minutes. Okay, can I hear 2 hours? 15 minutes. We'll see you in a bit.
I think we got everything, the technical difficulties taken care of, so we'll be able to continue. Mr. Carman.
All right, everybody. My sincere apologies for our technical difficulties that were happening up here. Some of the videos are not going to work so well. There's a couple that are important ones, and I'll get them working here in a little bit. So let's go back before I have a coronary up here. What we're talking about is in order to get heat released, which is what causes our damage, we have to get fuel molecules and oxygen molecules together. They have to have enough energy in them so that they basically fly fast at high temperature. And when they do, the molecules can collide. When the molecules can collide, then we will have sorts of chemical reactions that happen from that. Those chemical reactions in turn release more heat. We get more damage. Why is it that we go to some part of a room and we get real severe damage, and we go to other parts of the room and there's almost no damage, even though we know that's where the origin was? The reason is because at some point, after the original damage patterns were created, for whatever reason, that area either became devoid of fuel or devoid of oxygen. We no longer can have continued chemical reactions taking place there that release more energy and cause more damage. So we've seen how when oxygen and fuel gas come together, they can create things on this red circle. And for the guys on Zoom out there, my apologies. I wasn't aware that you couldn't see these screens up here, that you're just picking it up off the computer. So I'll try to describe it better. The red line that you see on the computer screen is the zone where the oxygen diffuses inward from the exterior, the fuel gas diffuses outwards, and where they basically encounter each other. If we were to look at this particular thing in molecular kind of terminology, what we have is a bunch of red molecules in the middle and blue ones on the outside. As they move together and they get closer and closer, we start to get the reactions where that red circle is. That's where the highest temperature is. That's where the damage would be created. Now, how do we work this into a building? We'll try to get into that here shortly. Phases of fire development kind of lets us walk through. And we'll try to get into how it is that we can look at a typical room and figure out what is going to happen with that fire development as we go forward. These are the basic ones: ignition, fire growth, smoke filling, smoke going out of vents, approach to flashover, and flashover. We'll go through each one. Early fire growth. Let's say we've got a room. We're looking at the side of it, okay? The thermometer on the upper left here represents the temperature in the upper part of that room, of the gases up there. So in this case, we just have oxygen, nitrogen, whatnot, and regular air. The temperature is kind of low. We have three fuels in this particular picture. It doesn't matter what they are. It could be sofas, it could be boxes of paper, it could be logs, it could be a pan of gasoline. Regardless of what it is, we're going to ignite one of them or get them ignited. All right, I'll keep talking. I'm back? Thank God. Whoever set this cruel joke up, I will get you. Okay, our fire starts and we get a development of a plume, which is basically hot gases. Those hot gases are more buoyant, just like in a hot air balloon. They're less dense, and so what happens is the more dense air out to the side kind of fills in behind and pushes them upwards. Again, just like a hot air balloon. So as those hot gases rise, they're going to rise until they hit that ceiling. When they hit a barrier, their movement is stopped, and they're going to have to move out to the sides. And that happens in what's called a ceiling jet. That ceiling jet continues until the hot gases reach the vertical barriers, the walls, and then we start to fill up the top of the room. As this is all happening, you now see these little blue arrows on the side. We get what's called entrainment. Entrainment is another word that as a professional fire investigator, you should really try to understand, because entrainment is very, very important to your fire development. The reason we get entrainment or mixing of cool air from the exterior, that plume, into the plume, think of it this way. If we have a stream, okay, just like out in a creek someplace, and we have water flowing down in a channel in the middle, and there's still water on both sides. What happens is the molecules from the moving water will interact with this still water, and it creates a drag or a friction, and we start to get what's like eddies to develop. So have you ever seen, I know you've seen this as fire investigators, you see a fire burn, and on the outside you get these little eddying effects. The reason is the movement of the fast moving molecules will drag against the other ones. We actually get physical dragging, which creates, and it imparts a motion and gets those spinning. And as that spins, it mixes in cool air from the outside into the warm air. Does a couple things. It cools off the air that's rising because we're now putting in something that's colder, but it also increases the volume of that air, right? So we'll talk about entrainment quite a bit. We got the flame zone down at the bottom here, that's essentially equivalent to the flame height. We have our plume. It rises up until it hits a horizontal barrier, and at that point we get a sealing jet. The sealing jet moves very quickly. Now there's no movement of oxygen into the sealing jet, because at this point there's really not a lot of mixing of the oxygen below it into the sealing jet. There's a little bit of friction, but not nearly like when it goes through that vertical pass in the plume. Now, what's called the entrainment zone is the area below that sealing jet down to the base of the flame. Now, again, the oxygen doesn't move vertically into the sealing jet or into the smoke layer. It doesn't get entrained that way. It gets entrained into the plume, which for all intents and purposes, pumps it on up. All right, it's that vertical friction that drags it and pumps it on in. But as it moves out to the side, it doesn't have that same effect where it's really getting a lot of mixing up there. Now, for the folks in the room, I know you can't see it in Zoom land, but this area right here on the underside of the sealing jet is what I'm pointing to. There's not vertical mixing. There's mixing here in the side. What happens is as this smoke layer drops down even further towards the fuel, the entrainment zone gets shorter. As it gets shorter, the area over which cool air is entrained reduces. So the rate of cooling now of the plume reduces because we're putting less cold air into it. All right, we're putting less fresh air into it to continue to oxidize anything that's left over that didn't get oxidized in the flame. And entrainment is going to get slower and slower. Okay, here we have smoke filling. You can see the smoke dropping down or descending from the top. It fills the upper volume of the room. Notice on the thermometer to the left of the room, the temperature starting to go up there. What that means is that the smoke area up there, the volume of smoke is starting to get warmer. We still have entrainment, but now notice the entrainment zone, which goes from the underside of the smoke layer to the base of the fuel, is shorter than it was in that last slide. So we get less cooling or a slower rate of cooling than we had before. Smoke continues to bank down. As it's banking down, the temperature of the smoke is going up because the fire's pumping more energy up into it. The temperature, as we see on the screen here, to the left goes up a little bit. The smoke is going to transfer heat by both convection and radiation into the ceiling and into the walls. The walls are going to heat up. Now we've dropped our smoke below the vent, so some smoke's going to escape. As the smoke escapes, the vacuum that is created is going to pull in air at the bottom, cooler air. One thing to remember when we're looking at this movement that's very important is the mass that goes out of the room, the mass of smoke and hot air that goes out of the room has to be equal to the mass of air that comes into the room at the bottom. Okay, now think about this. If I have an area this big that the cold air is coming in, all right, through a doorway, and I only have this much of the area where smoke is going out, the smoke or the cold air that's coming in this big area can move a lot slower than the hot gas going this direction because it doesn't have to go as fast to equivalent the mass. The mass of the smoke equals the mass of the cool air. If you got a bigger area, the cool air can move slower. As this smoke layer drops down farther and farther, the speed of the lower zone increases and the cool air goes faster and faster to be able to match up with the mass of hot gas going out the top. This does get to be important that we'll talk about. Continue to heat this room up. When the temperature up top gets around 11 or 1200 degrees, we have enough radiation from that hot gas to go down to the other fuels, cause them to release gases, and then they will eventually burst into flames, leading us to what we know as flashover. Somewhere in this point, right around here, we have switched from fuel limited burning to ventilation limited burning. Not exactly at flashover, might be just before, might be after. Has to do a lot probably with the size of the openings that the air can come in, the amount of fuel, and so on. All right, here we have a room that we're going to say it's in flashover. At this point, the temperature in that upper layer, unfortunately, these slides, I switched from Fahrenheit to C. Celsius here, instead of 1200 Celsius, let's call that 20, am I dead? No. Let's say that's somewhere up around 2200 Fahrenheit, or 2190, that's pretty close to 2200. The mind isn't completely fried, so whoever did this to me, you bastards, you'll get yours. No, I'm kidding. So about 2200 Fahrenheit is going to be the temperature in the upper part of that room where the flame is showing. Now notice that the flame is now shown as extending steadily out the door here. Why do we go from a slide like this where we have just smoke showing to this next slide where we go to where it's flame showing? Sorry? That's where the air is, yeah. The air was there before. Why is it now flame and it was smoke before? It's because, think about the fire triangle. We have gotten it to the temperature where it can now just burst into flames and auto-ignite. Before it was cool enough, it wouldn't auto-ignite into flaming combustion, it would just stay as smoke. But as soon as we get up towards the flashover zone or transition area, we now have hot enough gases that all they need is oxygen to burn. When they get out of the room, they encounter that oxygen and they can actually go into flaming combustion. When we talk to our fire crews and they show up on scene, one of the important questions to ask is, did you see steady flaming coming out of any of your openings, any of your doors, your windows, things like that? If they're able to tell you when that occurred, that's a fairly reasonable estimate as to when flashover started in that room. Because at that time is when you'll start to get that flaming combustion. All right, we're looking kind of at what looked like that candle diagram before here. All right, just superimposed. I'm going to expand it out to where it takes over most of the compartment. I'm doing this to look at the molecular point of view. For our diagrams before, what's going on inside that compartment right now is a lot of combustion has taken place. We have a lot of combustion products up in there, but we don't have much free oxygen. The free oxygen is outside the room. It's coming in at the bottom, and the hot gases are going out at the top. Where those two lines pass each other on that red line again on our candle represented our reaction zone, that again is our reaction zone here. We're having hot gas go this way, cool air come this way, and where they pass each other, they mix really good combustion. It so happens that in a room like this, where we have this setup, the highest temperatures in this room are right along that green arc, right? Because that's the zone of combustion. And this may seem a little disjointed, especially with the difficulty I've had here trying to point this out, but the purpose of showing you these molecular slides and all of these kinds of things in the chemical reaction is to stress to you to try to think about where is it that we end up with a lot of fuel-rich gases in the vicinity of oxygen rich, oxygen-rich gas, so that the two can combust, because where they do combust is where the heat is generated. And where the heat is generated is where our damage is going to occur. Years ago, people first tested out this idea of flashover causing damage on the floor. I don't know if there's many of you that were around in the early 90s, but there were a series of tests out in Florida done after a homicide charges were filed on a case. They thought a guy set a fire that killed some people in a house. It was on a place called Lime Street. The question was, could the patterns we see on the floor be something other than flammable liquids? That was the issue. This is clearly the result of a flammable liquid pour. So what they did was they were lucky enough to have two buildings that were similar size right next to each other. So in one of them, they set a fire using flammable liquids on the floor. The adjacent building, they set a fire using just common combustibles and let it go to flashover. And what they found was when the flashover situation established inside, the hot gases got to the floor, the fresh oxygen came in at the bottom, they were getting worse damage from the flashover conditions because of this mixing along that green arc at higher temperatures and more damage creation than they did when they had the house with the flammable liquids. And as a result, they dropped the murder charges. Because what they realized was we just don't recognize what we're seeing. Now, it is a common perception that flames are always going to burn over the top of a fuel that gives off those red molecules. I want to show you a video here, and I hope it's going to work, where we will display a box. On the right side of the box, there are two panels that can move vertically. That gives us a gap at the bottom and a gap at the top. Inside the middle of this box, we have a pan of similar to gasoline, a liquid similar to gasoline. We're going to ignite that. The flames are going to come up. And what we're going to watch here is, if I can get this to work. Bingo. Oh. We're going to get this fire to start to burn. Now, watch what happens is we're looking at that pan of gasoline that's been ignited with a spark. We have the lower section to the right open at the bottom. The upper section is our exhaust where the hot gases are going to go up and then move out to the right. Notice the flames when we first start this fire. They're going to bend over towards the left. Let's think about why that happens. Think about our airflow and our fluid flow in here. The hot gases are going to go out the top, creating a vacuum, and an equal amount of cool air has to come in the bottom. As it comes in the bottom, it basically just tips those flames right over. All right? But let's watch for a few minutes here. Yeah, it's getting starved for oxygen. there's a vortex on the pan? And what we'll see is that the flames completely detach from the fuel and they get established very steadily over by the oxygen source. But what we're seeing is still combustion. It's the combination of fuel gas and oxygen. The problem is there is no oxygen where the pan is. Our pan is our origin. Our oxygen is somewhere else. We get this compartment so loaded with fuel that we become ventilation limited, and the flames actually depart from the fuel source and go over to where the oxygen is located. Now, at this point, tell yourself or ask yourself, where's the damage going to be occurring? Is it going to be occurring primarily at the origin? Or is it going to occur where the chemical reaction takes place that releases the heat? This is the kind of conditions you will see in a ventilation limited compartment a lot of times. The one difference in the compartment like we had in Las Vegas is that we had so much momentum with that cold air coming in the bottom through a small zone. It was moving so fast that it made it further into the compartment because we had so much more hot gas coming out the top. So again, we have to make equivalent amounts of gas going out and in. In that case, we had a much larger vent at the top, much smaller at the bottom. Here, it's the same size top and bottom, so the speed is about the same. Once we have the gas in this pan consumed, what you'll see is the flames will just start to flicker and move around a little quick, and then they'll go out. But you're looking at a ventilation limited condition that is burning primarily where the oxygen is located. Any questions from anybody or the Zoomers with regards to this, Jeff? Sir. Okay, the question was, what will happen if we have more oxygen or less oxygen coming in as compared to hot gases going out the top? If the inflow comes through a smaller area than the outflow, the inflow's velocity has to be faster. That was magic. So what happens is, as it moves in more quickly, it will bend the flames over. Is that right? Okay. I'm showing it here. The slide's up right there. Okay, we're back. Thank you. So we start off with a whole bunch of blue oxygen molecules up in the top. And we also have 78% nitrogen. This is 21% here with the oxygen, but I got rid of the nitrogen just to make it clearer. Once we start this and we put a pan of gasoline, the gasoline's going to start to evaporate and it's going to start to release red molecules up, fuel molecules. They'll get together. We add the heat, which got the reaction started, and suddenly we start to develop our combustion product. The red and two blues is carbon dioxide, and the straight red ones are the fuel, and the blue is the oxygen. So it starts to build up, until we get to the point where we have a lot more fuel being evaporated. We still have combustion products which tend to go out to the top because they're warm. That creates a vacuum pulling the blue or fresh air molecules in the bottom, like that. If we vary those heights of the vents, like your question was, then we'll vary the velocity, the relative velocity. And Jeff, did you say you had Zoom questions? Okay. Yes. Okay. Right. Okay, the question was at the break they were talking about entrainment, and they said, let's look at our Vegas fire. Let's say we take an ottoman and put it at the foot of the bed. All right, it's not in the doorway, but it's in the foot of the bed. So hot gases develop, they're going to go out the top, drawing in fresh air. Is the fresh air still going to be able to support combustion at the base of the bed? And the answer is yes, but we have to think about, it's like water in a stream hitting a rock. It will go around it. I think what you might find is tremendous amount of damage in the back of the ottoman. I mean, as the air's flowing this way, it gets to the back and starts to spin. And when we get that spinning, we get really good mixing, like we talked about earlier on that little tornado-like thing. Anytime you get really good mixing, you get very efficient combustion. Now, you still will get some combustion before, but that tornado type of effect really does good things. So you'll still get damage. You'll get damage where we can mix our fuel gases up top with the oxygen down below. But anytime we can get this kind of mixing as well as the shear kind of mixing, it's very effective. Answer the question? Jeff.
Steve, will rollover conditions within a compartment present differently to an investigator versus flashover?
Yes. Rollover is essentially ignition of fuel-rich gases that are in the compartment when there's still enough oxygen there to cause that fire to move towards the door or towards a vent, much like we saw in that last little video. Okay, as they go through, a rollover condition is typically a very short-lived condition. And I say short-lived, I don't know if we're talking 10 seconds, 20 seconds, 5 seconds, but flashover could go on for minutes. So when it happens, you still will have heat transferred to the ceiling, to the walls, to the curtains, whatever the case may be that's left over to burn. But with a flashover, you're not only having the convective energy transfer of these moving gases, but you're going to have the radiation heat transfer. And the fact of the matter is radiation transfers heat far more efficiently than convection. So the flashover type conditions will be more conducive for damage generation than would the convective heat transfer of a roller. That answer the question? Okay. Okay, so we're going back to the Vegas test there. We see this pattern on the wall because we know right below is where the fire occurred. The other thing we know is that much like our box that we were just looking at a little bit ago, as the fire progresses, this area where that V pattern is becomes very fuel rich or very rich with combustion gases. But what it doesn't have is oxygen. So let's think about this in terms of people say, so what does all this mean, this hypothesis testing and development stuff? Here's two hypotheses, okay, for that compartment. I'm going to hypothesize that one of my fires occurs right at the back wall where that huge pattern is. All right, so let's test that hypothesis in a short way. Let's say, could that pattern have been created if I poured gasoline on the floor? Or I try to disprove it. Let's say, I say, well, the pattern couldn't have occurred unless I poured fuel on the floor. But no, that's not true. Because if I'd had fuel gases throughout the room because of burning elsewhere and releasing a fuel gas. And now I have oxygen flowing into that door to replace the hot gases going out. I could get mixing at that back wall, could get the chemical reaction to take place, heat being released, and a huge pattern developed. Okay, so that doesn't necessarily mean it had to be the origin. Now let's look at this and say, okay, my second hypothesis is this is the origin. Could ventilation have caused that pattern? Or would that have had to happen in a fuel limited type of condition? So the fire starts there, okay? The room fills up with hot gases. Gases are going out the top of the door. Fresh air's coming in at the bottom. Would the hot gas, the air that's coming in the door suddenly take a left turn and go back into that corner to cause only that pattern? That doesn't make a lot of sense. That fresh air that's come in is going to go straight because it's got a lot of momentum. It's not going to suddenly get around the back of the bed and take a left 90 and go another 6-7 feet and only burn right there. This most likely occurred when there was plenty of oxygen there early on. And if there was plenty of oxygen and we have that damage, that's indicative of, well, maybe we had early burning there while there still was plenty of oxygen. Does that answer all your questions? No, but it at least lets you start to think about how to proceed with looking at patterns like this and considering them in light of oxygen flow. Correct. Sure. The question was, I talked about at the FRL between test 1 and test 3, the area above where the fire started had gotten sooted over. And so we tested damage to the wall through depth of calcination measurements. Basically took a little tire gauge, tested the depth, how crumbly that wall was. You could tell that over an area about this big, that wall was falling apart in essence. We could get a deeper probing with that tool than we could on good, fresh gypsum board elsewhere. Terry asked, is that a good kind of tool or good process, perhaps, good technique to use during these fires, post flashover? And I'd say yes. It is interesting. You mentioned that. Just to give you an idea, the depth of calcination we got over there was about, as I recall, 2 to 3 millimeters of depth that we could get, as compared to nothing on the unburned areas. But on the big pattern on the back wall, we were back 6 and 7 millimeters. Why was the damage there so much worse if it wasn't the origin? Well, that's where we had more and more oxygen throughout that fire to be able to continue to combust the extra fuel gas that was flowing around the room and release more heat. Does everybody understand that? Because this is kind of the crux of this idea. Right. The question was, or the statement was, that could be a double-edged sword and lead you to think that's where the origin was because that's where the most damage was. And that's exactly the point, Andy. We need to make sure that just because we see an area of more severe damage like that, we don't automatically try to make that leap and say, oh, this had to be where the origin is. At that point, we need to start hypothesizing and testing, is this area of severe damage an area where we might have had a lot of oxygen flow late in the game when there was plenty of heat and plenty of fuel gas? And if it is an area where the air would be flowing, we can't then make that conclusion, oh, this had to be the origin, right? Now, here's a real tricky part. Let's say we'd started our fire right in the middle of that pattern. Okay, the fire burns, it gets into the bed, it gets into the chairs, it fills the room up with gas, it turns to flashover, and now the air comes in. and it creates a big pattern back there. Well, now we're kind of in a pickle because, yeah, that's our origin. Can we prove it? We're getting pretty challenged at this point. We better find something else. We better hope we find something else, because patterns alone at that point, much like that slide I put up there earlier, they don't always give us the answers we need. Patterns alone. That's when we have to start thinking fire dynamics, the science, the fluid flows, heat transfer, and all that kind of stuff. The totality, exactly. Okay, so you say, I don't know exactly how air flows in these compartments. How do I test to find out how the air is going to flow? All right, this is a jump back to an earlier slide where I said one of the ways you can do hypothesis testing, perhaps, is using fire modeling. On the Vegas fire, I decided to fire model that to try to figure out what the airflow was. We'll stop real quick and I'll talk about fire models. Fire models are not the end all to give you answers. They're not terribly accurate. Jim Quinteri of the University of Maryland once said, the definition of a fire model is a computer program that makes really neat cartoons. And that was about his respect for fire models. He thought he could do every bit as well with calculator and pencil than these computers could. Fire models are based on weather forecast models. It's the same basic structure. And we all know how good weather models are sometimes. But what they model really well is the flow of air and flow of fluids. If we use fire models to model the flow of fluids, we'll be in much better shape. And let me show you what I mean by this. This modeling was done by a computer model called Fire Dynamics Simulator, put out by the National Institute of Standards and Technology. It's a free software. You can go to the Society of Fire Protection Engineers and learn how to use it if you want. It's a complicated model. It takes a while. But once you use it, you can get some pretty good information. And I'm just going to buzz through this because we don't have a lot of time. Now, Dan Heenan is standing right there. He's going to be teaching, I believe, Wednesday or Thursday. Wednesday. Okay. Along with, who else is teaching that morning? Oh, yeah. So Dan is taking some photos in the actual compartment as it burned 60 seconds into the fire. We modeled it. The lower box here shows how the model estimates the fire would have progressed to that point. 3 minutes, the model is showing the hot gases are going down, smoke is coming out. In reality, we see smoke is coming out. Now, the difference in the model and real life is the model doesn't depict time nearly as well. What it does, though, is if you can associate the time that the model thinks flashover occurred with the actual time flashover occurred, the progression of the fire is pretty similar. It's just that the time isn't right. So, in other words, the model thinks we hit flashover at 278 seconds. We hit it at 210. Okay, at 278 seconds, the model says, okay, we're in flashover, and it shows flames everywhere. In reality, we don't have flames everywhere in the real life picture up here. We continue on though, and we get steady flames from the real fire, which kind of matches up where the model is. So understanding the time is a little off, you can still get some good data from it. Here's an example. This is looking into the room from the bottom of the bed. We're looking up towards the origin of the fire. This is at 60 seconds into the fire. The model estimates the hot gases that are coming off the initial fuel may have reached the ceiling and started to spread out. I got rid of the smoke so we don't have to see it there, and we can see what's happening with the flames. At 120 seconds, fire has spread across the bed. The hot gases have come over and ignited the top of the dresser and so on, and the fire is burning by 290 seconds. Look where our flames are actually located. Remember, the model thinks we went to flashover at 278 seconds, so this is 12 seconds later. By this time, the model thinks the actual flaming combustion is in that arc along the floor up to the back wall and to the ceiling. Why is that? That's where the oxygen is, right? The oxygen's coming in at the bottom and gets all these fuel-rich gases, hits the back wall, starts to spin and mix. And so we have good flaming combustion everywhere. Blue and red molecules match or mix.
A question from the Zoomers. Is the damage on the back wall, and that would be, I'm believing that's the wall above the bed,
Oh,
more likely to happen in a narrow room?
can you narrow which direction? And which is the back wall?
He's got a, is this back wall and he's got far wall, which I believe.
Across from the door.
I'm not sure if he's referring to across from the door or if he's referring to back over behind the bed.
Well, maybe you can ask that question again, but I'm going to try to define it as I see it.
Okay.
As if you had a narrow room, let's say, and the doorway's at an end of the room, okay? So the long axis is where the air flows, okay? And the room is full of hot gases. We know that the doorway is a certain size, just a fixed size. Say it's the same as any old room. So we know if the area of the floor in that room is the same as what we see, okay, but it's just longer, narrower type of thing. What will happen is it should take ballpark the same time to hit flashover. Maybe a little less because walls radiate back and forth, but once we get to flashover, we still have the same amount of hot gas going out the top of the door, which means we have the same amount of cool gas coming in the bottom of the door at the same speed as it would with our version here. Knowing that that cool gas that's coming in has a certain amount of momentum, which is mass times the velocity. Okay, and we know those are fixed basically at that point. We know it's got certain momentum that's going to carry it into that room. And as it's being carried into that room, it's going to be consumed. It's going to be turned from oxygen into carbon dioxide and water, okay, as it goes through a chemical reaction. How long does it take for that consumption to take place? I don't know. However, what I'm thinking is it may be consumed before it ever gets to the back wall. And if it is, then the heat will be released closer to the door and we may not get the damage on the back wall because we don't have that oxygen making it all the way back there and then doing the mixing.
And you caught it because he followed up with across from the door. He also asked, would you expect there to be a lot of mixing with the incoming combustion air with the products at
Coming
the
out.
back wall all the way down to floor level? Are
Yes.
you going to be able to carry that all the way across at floor level until you get there to the back?
In general, I would say if the room is similar in size to the rooms we're seeing here, yes, I would expect to see it all the way to the back wall. However, if that distance increases to get to the back wall, I'm going to think that maybe we're not going to get the mixing. But I'd have to do some tests, and the way I do the test is fire modeling. I'd put that compartment in a fire model. I'd say, okay, we got enough fuel to set this thing into flashover. Let's see how far back the oxygen goes.
Would that also be governed by obstructions?
Yes. Yes, much like your question earlier, if we put an ottoman at the end of the bed, is it going to interrupt that flow? Let me go on just a second. Maybe it'll answer some of the questions as what the model can do. So what we see here is an arc of flame, okay? This next shot, the next few shots are indicative of a representation of the heat flux. Heat flux is the intensity of the temperature onslaught against the walls, the energy onslaught rather, against these walls. In this case, green is a higher heat flux early on in the fire than blue is. Blue is kind of like just cool, normal conditions. Where the green is, it's hot. Where the yellow is, it's even hotter. If we see red show up, look out, because it's cooking. Okay, so early on, 60 seconds, we start to see the hot gases develop like we showed in earlier slides. The intensity starts to cook that upper corner. With time, that initial fuel package starts to die off because it's only a bucket of paper. By now we got hot gases which are heating up the bed and they're heating up the top of the dresser at the end of the bed. With time, the fuel on top of the bed's going to burn away, and the flame front continues to move to the south. Now, this says 240 seconds. I told you flashover was estimated at 278. So let's look at what happens at 270 seconds. Not much different than 240, okay, a little bit. We've burned out a little bit more of the bed. But now at 280, look what happened. Remember I told you the red is super hot, super intense conditions. We're starting to develop that on the floor and on the back wall. We're starting to see yellow this way, and with some more time, another 10 seconds, look what happens. Because of our air that's flowing through that door and hitting the back wall, encountering all this fuel-rich environment, we're getting this incredibly intense heat. The intense heat is going to create the damage. So it just continues. But look what happens back by our origin. What's our intensity back there at this point? Not much. The last slide, not much. The slide before that, not much. All the intensity for the damage creation has been moved over towards the path into the door and up against that back wall. All right, here's another top-down view. Okay, here was at 270 seconds, 8 seconds before I thought we went to flashover. And as soon as we get into flashover, look, all the flame, the body flame moves over in these ventilation limited conditions to where it's really capable of burning in the airflow. And it stays basically along or aligned with that airflow. This is oxygen level. Red means 21%. That's the standard oxygen percentage. Look, 8 inches off the floor is what this depicts. When we start off 3 minutes into the fire, at the top left corner, we're starting to deplete some of the oxygen up there, but everywhere else, we've got really good oxygen concentration 8 inches off the floor. 60 seconds more go by. We still have really good oxygen, but when we get close to flashover, look what happens. Now, the blue areas are zero oxygen. So we have now eaten up the oxygen or consumed it in the back left corner or the top left and the bottom left corners. So can any more flaming combustion happen in those areas at this point? No, there's no oxygen in those areas. So we can't have flames. If we don't have flames there, we won't have the kind of damage production that we would have in flaming conditions, and so on. Now, if we look at the, I'm going to go past this real quick. We don't have time for this. Well, I don't have the pictures here, but when I showed a view of the heat flux from the doorway looking to the back, what we find as I progressed the slides, it showed this red damage on the back wall. And when I went back to the photo, it matched up miraculously with the actual damage that we observed. So it is a very effective thing. I somehow got out of this presentation. Okay, so we're going to go past that. How heat flux varies with location and time. When we start off, our molecules would look something like this. A lot of red ones in the back left by the trash can and a lot of blue ones to support combustion. As the fire progresses closer towards the flashover condition, we now have a lot of unburned fuel molecules over in there. Not a lot of oxygen to burn them, but we've got a nice flow of oxygen through that door, and anywhere along that path we can support combustion and, again, a lot of heat production. Okay, we don't have time for doing this. I want to get into this next example of a case here real quick, because I think it's a very important case for us to discuss. Okay, so maybe you can help me here. I'm trying to find the other files, of the other PowerPoint files. They're not even there. Video files. So Oh, that was there. Oh, my God. Okay, I'm transferring some more files over. Let me tell you a little bit about another case that came up. I want to discuss this because this is it was a real life case. It was a criminal case. However, I was not hired to look at it for a prosecution point of view. I was actually hired after I had retired from ATF. And I was asked to look strictly at the fire because the allegation was a man had killed his wife in a fire and had been arrested. He swore up and down he did not set a fire. And so the question was, could we look at the remnants of the fire and try to figure out if he was telling us the truth? Try the bottom. Yeah, please. Oh, you get rid of it. That's fine. Okay, great. Thank you. Okay, here we go. This is a two-story apartment fire. It happened in 2011. And yes, this is a Monday morning quarterback analysis that we're going to go through. There we go. Thank you. So here is our analysis of this fire. It takes place in this building right here. It's a two-story apartment. To the right, upstairs, are bedrooms. The two windows to the very right are mom and dad's bedroom. The large three-pane window or three-panel window in the middle upstairs is like a family room, and the double panel to the left is their adult son's bedroom. Down below, you see three panels kind of lined with up top there. Those are, that's a living room, and the door just to the left of that is the entry door to the apartment. Okay, so this is looking down from the top. At the very bottom of this you see kind of a green square. That is a sofa underneath that big window that comes in. Just to the left of that is a door, and I wish I could point for the Zoom people that you could see this, but I'm going to point for the folks here in the classroom. This green lime or blue-green rectangle is a sofa. To the left of it's a door. Straight back, we see kind of a golden brown upside down U. That's the kitchen. In the kitchen, to the left side is a stove. Behind that wall where the stove is a laundry room. Okay, the other side of the U to the right opens to or backs up to a dining room. And then around to the right, on the right wall, coming back towards the bottom, we'd actually be climbing stairs to the second story. This is part of a diagram that was done out of a fire model. That's why it's not terribly smooth. Here's a little better picture. Kitchen, center top left with the brown and gold. All the way to the left in the center is a laundry room. You can see the stairs on the bottom right. Now you can see the sofa at the bottom, the door just to the left of that. The green or the same blue-green square at the edge of the kitchen is a recliner. Okay, so here's the story. We'll try to go through it quick. Mom and dad go out partying one night. They really like to party because when they come home at 5 o'clock in the morning, mom is absolutely ripped. She is later found deceased with a 0.28 blood alcohol, cocaine, and pot on board. So she's pretty well lit up. Yeah, yeah, she hit the trifecta. Dad was also heavy into the booze, cocaine, and marijuana, but we never got the numbers out of him because he didn't die. But when they got home, she continued to drink. Dad, being an upright guy like he is, decided he didn't like that, right? She shouldn't do that sort of thing. So he got mad at her. And when this little dad couldn't get this larger mom to pay any attention to him, he choked her, right? Grabs her by the neck and chokes her. Well, she didn't like that. She didn't do well with it. She got bruises around her neck, but it didn't break the hyoid bone, and it didn't cause her severe, terminal problems. Like that didn't kill her. All right. She's clothed. She chews him out. He takes off upstairs. Dad is a creep. I will tell you that right now. Okay. He went upstairs and he went into his bedroom, which is over the top right of this picture, kind of at the base of the stairs, straight up. We know he went in there because when he went in the room, he didn't want mom to come in. The son reports him dragging a mattress and box springs in front of the doorway. Why do you drag that in front of the doorway? Well, he got mad earlier and ripped the doors all off the hinges. So there were no doors in the place. Just blankets and sliding mattress and box springs blocked the door. So he's up there. Mom stays in the kitchen. The son is at the bottom left of this picture, but on the second floor. Okay. Time goes on. Half hour, an hour goes by. We don't know. The son reports hearing mom screaming. She's screaming at the top of her lungs. He's never heard anything quite like it. He said he just assumed it was a drunk scream, but they'd been fighting much and he's so sick and tired of them, he doesn't go downstairs to investigate. So pretty soon the screaming stops. He never hears the bed blocking dad's door being moved again, so dad could have gone back downstairs. So he thinks dad's still in his room. A few minutes later, they detect smoke upstairs, and it's getting thick, and it's getting black, and it's getting hot. So dad in the top right part of this picture decides, I'm out of here. He opens the window and dives out the window wearing his Superman pajamas and boots and no shirt. This is in December in a very cold climate. Dives out into the snow. The son, who's down here at the bottom left, around this area, he knows the smoke's coming on. He's got a baby girl in the room. He needs to get her out. He's yelling for his dad. The dad comes around to the front of the apartment on the ground floor. He's screaming, how could you do this? How could you do this? And the son's like, hey, up here, pay attention. I've got a child to hand to you. Get his attention. He hands his child down. He calls 911. Fire department comes. They put the fire out, and they find mom. Now she is naked, and she's in the kitchen on the floor, deceased, on her back. That's the fact pattern. Okay. Dad, meanwhile, is a little cold in the Superman jammies and no shirt, so he hikes it out of there to his other son's house without telling anybody. So the cops show up. Dad's not there. Yet people had seen him earlier. He had been standing down here in front of the big window down below, banging on it. We think he might have broken that window at some point. Yet the lower floor was in flashover type conditions, and then flames came out, and as you can see, they lapped up to the upper floor. Okay. Meanwhile, Dad's gone, but only after he does manage to get the child from the top left window in this photo. Mom's 41 years old. She's got a carboxyhemoglobin of 60%. Blood alcohol, I exaggerated, is only 27%, not 21. Cocaine and pot on board. Dad, son, and son's infant daughter were upstairs. They all escaped. I mentioned this. The dad was found at the other brother's apartment an hour later. They get mom out of there, and at the autopsy, she's not burned hardly at all, even though that room was in flashover. She does have bruises still on her neck. So it's like, dear old dad, come down to the police department. We want to talk to you. When they get him down there, they said, how did she get the bruises on her neck? And he said, well, I choked her out earlier today, but I didn't kill her. Well, then you set the fire, right? No, I swear I didn't set the fire. I said, why would I set the fire, then go upstairs directly over where this area is, just hang around in my pajamas, and then dive out the window with no shirt on? Does that make sense? Well, they did some more investigating, and they found out that he'd had a history of choking her and beating her up for years and years. Public scene investigation comes in, it ends in December. Private investigation starts to come in about mid-December and does its stuff. In 2012, all the electrical artifacts from downstairs were sent to the ATF lab. They were found not to have started a fire. There was nothing wrong with the electrical artifacts throughout the living room and the dining room. 2015, these investigators traveled all the way back to Chicago, where mom and dad were from. They were back there attending the IAAI conference, where we were teaching a class, or I was teaching a class on elevated fires. The investigator sat through my class. I said, be very, very careful of elevated fires. You have to be super cognizant of weird damage patterns that can happen. So investigators talk to the family. The family says, Dad is a bad guy. He's beaten her up for years. He's no good SOB. Lock him up. They go back to Alaska, go convene a grand jury, indict him for murder, arson murder. And he's arrested in the fall of 2015. These are some of the quotes that came in the investigator's report. He said, on arrival, crews discovered a well-vented working fire. What does that mean in terms of flashover and ventilation limited? Working ventilated fire, probably in flashover. We probably are in ventilation limited condition. The PD officers learned of other victims from the fire apartment, and the other victims said things aren't adding up. So being typical cops, their antenna go up and they get alerted to what's going on. The fire investigator next receives a call from the PD sergeant who tells him, Dad ran from the scene and he was found at somebody else's apartment a mile away. This is the top picture, or the top window in this picture. Slightly to the left is where Dad dove out. There's a window right underneath there at the bottom of the stairs, which is almost directly underneath his window. On the back of the house at the right, this is important, there's a small window with a little smoke coming out of it. That's the kitchen window, which never broke during the fire. There's that window again, just on the lower side, left of center. Okay. So the fire investigator testifies to the grand jury. I'm also a member of the IAAI. I recently traveled to Chicago for their conference. It's ongoing training. I do all the neat things I need to do for education. DA says, how many fire scenes have you done? Oh, I don't know, 300, 350. And he describes how he investigates. I try to determine where the origin of the fire started. Then I go from the area of most damage, least damage area to most damage, and I work on trying to determine the area of origin. Okay, let's stop right there. Will traveling from the area of least damage to most damage take you from somewhere else to the origin? Based on what we've talked about today, is the area of most damage the origin?
No.
Not necessarily. So by going from the area of least damage to most damage, you might be going from the origin to the door. You might have located where the air source was. Okay. He's going to go through this scientific process, and then he's going to develop some conclusions. He's going to find hypotheses and test them and try to eliminate them. And if they withstand elimination, he'll make a final selection. He's saying all the right things. He knows what he needs to do. This is the kitchen. We have a stove to the left. Remember, dear old dad was just a household trimmer. 3 of those burners did not work on the stove. The only one that worked was this back left. The front right didn't even have a burner element in the pan. Okay? This is obviously before the fire. When they had the fire, they opened the front door and they looked straight in. And this is going to be hard to do for the Zoom folks without, but I'll do it. I'll point these things out for the classroom. Notice the refrigerator's got a door open right in the center of the picture. See how the damage kind of slopes up to the left? It goes from bottom right down low and it slopes up to the left, almost as if the fire is moving from the right to the left here, okay? We can see 2 cones kind of in the left center, and right behind there is mom's body. We have a cabinet on the left side, again, a kind of a V going up to the left from over by the refrigerator. Notice in the kitchen, most of the sheetrock is still there. So this picture is in the direction of that arrow. We can see the wall next to the door. There's a door on the left. You can kind of see looking out, and you see how the air has come in and creating clean burn on that wall. The investigator properly recognizes that as a ventilation pattern from air coming through the door. To the right of that pattern, let's go back. To the right of that pattern is the entrance to the laundry room. To the right of that is the kitchen, okay? Now we're standing over to the right, looking to the back of the room. We see this big pattern on that back wall. That wall is in a corner next to the kitchen. The kitchen has an open pass-through just to the, how do we say this? About 3 feet out from the back left corner is an opening where you could pass food from a kitchen to a dining room. That opening is about 3 by 3 ballpark. And there's a sofa at the very back wall, straight ahead, near where the real bad pattern against the wall or back corner is. He describes that as this area right inside here is the northwest corner of the living room where I believe the fire originated. He calls it living room, sometimes dining room. But what he's talking about is this corner right back there, left to center. The next shot is, again, where the arrow is. It's pointing right towards that opening into the kitchen. There you can see it. To the right of that opening into the kitchen is where the investigator thinks the origin is, where the most severe damage is, his opinion. We're looking back directly into that corner now. Again, he sees damage close to the floor. It's fairly intense. Looks at the sheetrock and says, that place has been hammered. Now let's stand over by that opening to the kitchen and look towards the other wall. And we see the window that goes outside, which was right underneath dear old Dad's bedroom window. When Dad dove out his window, he would have gone right in front of this one. To the right, you see the stairs going up. Right? Now we're looking up the stairs. So you can see that there's really nothing blocking hot gases from going up those stairs. Off to the very right of the photo in the back is the front door. Then you have the front picture window right next to it. Now we're standing back there and looking towards that picture window again, and you can see that area a little bit better with the sofa right underneath the window. The remaining sofa. The motorhome is right behind the picture window, and the door's off to the right. Two more shots, or another shot of that. So now we're standing and looking where the red arrow is, basically at the staircase. There's a sheetrock wall and a the sheetrock has been taken off the wall which abuts the kitchen. Notice there is one stud channel, two channels over from the distribution panel. And I don't know if you can see it real well in this picture, but that thing is hammered. It is burned very badly, bad char. The only electrical line, branch circuit that goes through there has all the insulation burned off. It turns out that that branch circuit wiring in that stud channel is the only place in the entire apartment that the private investigator found an arc on the wiring. This is very important. Only place they found an arc. So the investigator for the city says, this is your panel, blah, blah, blah. The reason over here to the left, you see this charged stud cavity is right above it. There's a hidden spot where fire crews had a hard time getting to that fire. So it burned longer inside there before they could find it and put it out. Let's look at that again. That's hammered. And he's saying there's a hole at the top, and because they had delayed extinguishment, it caused that damage inside the stud channel. Okay. There's the hole at the top. Stud channel. Again, standing at the front door looking into the kitchen one more time, we can see those cones. Mom's in the back. To the right in the circle is the recliner. That was an upholstered chair recliner right at the base of the refrigerator. A while later, they'd moved the refrigerator out. They brought a bunch of lights in. Mom's already taken out. Now notice the kitchen at this point, the ceiling is open. Back here in the last picture, the ceiling's, much of it is still covered with sheetrock. Okay, we go back to this one, and now a bunch of it has been opened up.
Yes,
There with the photos. Now he's describing the pattern on the refrigerator in essence, he says, it looks like a movement pattern traveling from right to left. Here's the picture again. So he's talking about fire traveling from the right of the refrigerator way down low and then moving up to the left. He decides that is a movement pattern which tells him the fire moved from the right or in that living dining room into the kitchen. And he says it's impacting the cabinets on the left side. So look at the cabinet again to the left of the red post, and you'll see kind of a V pattern going up to the left. It kind of matches that pattern on the sofa. On the refrigerator. Okay. And the question by the DA was, so you say it was essentially developing in the photograph right to left, which would be living room towards kitchen. Yes, sir. Okay, so here we're looking at the edge of that photo where the firefighter is standing back there. The investigator thinks the fire starts basically over there and then moves to the left into the kitchen, which is just to the left of that refrigerator. That's all the debris on the floor early on, the recliner, sofas, all that kind of stuff. Now we're standing right in front of the kitchen again, looking inside. The cones are still there, mom's still there, sheetrock's still there. So we go on in and notice the lower part of the kitchen. It's not burned at all in comparison to much of the rest of the room. We have bare wood. We see mom's body. She is not clothed. She had been clothed. We see the stove to the left side of the kitchen. That window there in the back we know was closed throughout the fire, although it had some smoke leakage around it. So this place really wasn't quite as bad as the adjacent room. Again, mom's not too badly burned. little bit of burns on her arm and shoulder. Another picture where you see basically almost virgin wood there in the back that's not really burned too badly. The red on top of the stove is the remnants of a George Foreman grill. Since the 3 burners didn't work, they had to have a grill on top of that stove to cook with. And there's your stove. The only one that worked was the back left. We're looking at the stove at the very top center of this. We're standing in the entry, kind of looking towards the cabinets. The top of the cabinet is tipped over. Somebody's ripped that cabinet top off, and it's on the floor under Mom. So the cabinet surface is off the cabinets, on the floor, and she's on top of it. There it is. Underneath it, it's nice and clean. This is a roll of toilet paper, that golden looking thing right in the center. That was on the floor, hardly burned. A bunch of spices had fallen down on the floor from the cabinets to the right. Look how good cabinets are, the kind of condition they're in. She's right next to those spices. So this is upstairs. Dad's bedroom's the top right, kid's bedroom is bottom left. We're standing at the top of the stairs looking in the direction of the arrow, and we see that room is completely hammered. The wall separating the family room from the child or the son's room is totally clean burned. The big window to the outside's to the left. So the investigator says, my initial hypotheses based on the patterns were the northwest corner portion of the living room, near the base of the stairway. These are his possible origin patterns. The fire originated in the middle of the living room at the stuffed chair, along the east wall outside of the closet, that's at the base or the side of the stairs, and at the couch along the south wall. Those are his 5 possible hypotheses for the origin. Notice where he does not guess the kitchen. Why did he not guess the kitchen? Well, because the fire in his mind moved from right to left. So it had to be out in the living room, dining room area, right? The kitchen, he later says, it just wasn't badly damaged. He thought about cooking. There's no evidence of cooking on the stove, no reported smells of cooking. Stove is found in the off position with elements missing. Well, that's a good sign. Oven's in good condition, no food cooking down there, so he ruled out the kitchen as the area of origin. Autopsy. The victim had soot in trachea and upper lungs. Therefore, she was alive at the time of the fire. There was evidence of strangulation. They found the bruises, injury to her lower back. They found her lower back, about this area, was really bruised at an approximate height of the kitchen countertop. So they assume, oh, well, that means Dad was not only choking her, but he was slamming her into that countertop so hard that the countertop fell off, got onto the floor. Repeated abuse witnessed by others, and testified to by family members. Here's Mom's neck. You can see the bruises on the neck just below the soot marks on the chin. Still very obvious when they did the autopsy that day. Her old dad was a prince. A little bit of burning there, not too much. Apparently, the black you see on the face skin was in large part stuff that came off. It wasn't like charred tissue. So the DA says, describe how you're able to eliminate everything but the living room. Well, here's what he says. In general terms in fire investigation, we search from least damage to greatest damage because it's been our practice that in compartment fires, the fire, where it originated, is more than likely where the most damage was. But he bases his opinion on. Okay, so we're going to review this case. We get called 3 years later, asked to look at this case. At the time the fire investigators went in there, the ceiling directly above the stove is still covered with gypsum board. You see there in the circle. Another picture of the kitchen. and see how the sheetrock had been taken off during the investigation over the living room, but not over the kitchen. Here's looking at the stove directly on. You can see the George Foreman grill at the bottom center. The cabinets up above the stove are really hammered and almost like a V. Got that kind of an angle there. Cabinets right above. Now you can see some smoke has gotten up inside those cabinets, and notice the gap around the exhaust pipe. For the people in the room I'm talking about right here, we've got a nice gap where hot gases can flow out. Two sides of the backing of the stove, glass is broken on the right side of the upright control surface. It's still there on the left. Another view of the stove, more severe oxidation to the right of the range hood up above. Again, the glass is missing from the upright in the back. Underneath, see the right side of the fan appears like it has a little bit more oxidation than the left. Doesn't necessarily mean anything. We have burning with a V on that cabinet on the corner. Okay, now we're looking up in the ceiling. The sheetrock has been removed. One stud channel up there has ABS piping that's starting to melt, and we also have wires up in there where the insulation's burned off. Remember, this area was covered during the fire department's investigation. This was opened up by the privates. What we see there is the sagging ABS pipe, which is directly in line with the stove pipe you can see near the bottom center of the picture, up into that cabinet, or up into that joist channel. That's the only joist channel with any charring. Either side's fresh wood. You see the charring there? Directly above the range hood. And note at the bottom, it lines up with a burned stud cavity in the laundry room. We go back in the laundry room, there's our stud channel that's burned. Just one. That gap up above it. The branch circuit that went through the wall was found by the private electrical engineer to be the only electrical arcing in the entire house, result of fire consuming the insulation and allowing the conductors to contact. Time-wise, 911 calls at 8:40 a.m., fire crews dispatched 8:41, first unit on scene 8:45, and by 8:50, truck 3 is on scene. Truck 3 handled the securing of the utilities. So there's that stud channel again. Let's take another look at it. The wire is arced. The channels on either side of it are not burned, just the one. That's the hole up above it into the cabinet directly above the stove. Inside of the distribution panel's in great shape, no problems in there. Here's the stove again. Let's take a closer look. Oh, one more thing, let's go back. To the left of the stove is a outlet where the arrow is. On the back wall there, where that yellow arrow was, you see the yellow arrow to the left. The back side of that, we've got a duplex outlet or a quad outlet where smoke is obviously being pressurized from the kitchen into that room. The grill, George Foreman grill, was found on top of the stove. When we removed the grill, we found several photographs under it in the front right stovetop burner pan. How many of you keep photographs on your stove? Oh, yeah, a couple guys. Okay, well, that figures. Yeah, no burner element, just the pan and a stack of photographs. Well, guess who the photographs were of? Dear old dad. Now, why would there be photographs on the stove of dear old dad right underneath the George Foreman grill? There's a picture of dad sitting on the stove, or sitting on the sofa. So the guy picks up the George Foreman grill. The pan sticks to the grill. They're looking at it. They're looking at the appliances next to it. The investigator says there was a blender, microwave, and some type of hot plate. All were in good condition with no signs of failure or heavily damaged. Even dad probably would have said that they were heavily damaged. Here's a blender, non-heavily damaged. Yeah, the cords going to the outlet, they said were non-heavily damaged. There is some other appliance. So here's the floor. Mom's on that floor originally. She's not burned. When the fire department comes back, ATF comes in and they take some photos. And look what's in the next to the wall of the dining room there as you enter is the George Foreman grill. And there's other pieces of evidence they're getting ready to collect. So there's the grill. Somebody had the thought that this grill is important. We got to do something with it. Well, they did something with it. They stuck it in the snow and just discarded it. It was found by the privates a week later. So we're going back now to the place they think the origin is, back in that corner. We have fuels in there. Nobody took samples of the sofa. Nobody took samples, period. They just looked at it, looked at the patterns on the walls. Eventually, they took the sheetrock off the walls. Notice the studs behind the sheetrock. Pretty pristine. How many people have seen fire set next to a sheetrock wall in a sofa, and then you take the sheetrock off? What do the studs look like behind it? They're usually charred. Some kind of, I mean, if you have a very long-lasting fire. In this case, that entire wall in the dining room was not burned. Those are the items that were taken for examination. None of those showed any evidence of failure. The electrical items. Unburned stud. This is a switch from the kitchen. Notice the smoke being pushed into the stud cavity from the kitchen through the switch, not the other way around. Okay, so here is our ground floor again, kitchen top left. That window to the top right eventually breaks out. Had the fire been where the red square is and that window breaks out and dad learns about it afterwards and he jumps out his window, he's jumping right through that fire, right through the flame. Even his Superman pajamas would not have stopped that flame. And we have the stairwell right there. So when the window breaks up in the front and the wind or the air is pulled in through the door and the window, where is it going to go? It's going to go to the area of least resistance. It's going to go over towards that window, possibly out the window and upstairs, right? Look where it does not go. The kitchen. So let's do our hypothesis testing again. Our hypothesis is the fire starts back where the red square is, and we see a big pattern there. Is it possible that the fire there is as a result of ventilation burning when we have a lot of fuel gases floating around the room? I think it's a very good possibility that ventilation moving that direction towards the stairs caused that damage. Remember, we had so much ventilation that went upstairs, it trashed the room up top. Very bad. The stairs were heavily trashed, and look at that window in the kitchen was never open. So the wind wouldn't have blown through there. It wouldn't have gone into the kitchen and just sat there and spun around necessarily. It's going to take the path of least resistance. Window in the bathroom wasn't broken. Right there is the stud channel that was burned in orange over the stove. It lines up with, I'm sorry, the joist channel. It lines up with the stud channel directly behind it where the only arcing in the apartment took place. Early in the fire, before the fire department secured utilities, because if you have arcing, you know you still have power. Let's look at the molecules here. If we have a lot of red fuel molecules over to the left later on in the fire and all the blue ones are going to the right, those red ones are not necessarily going to burn and release a lot of heat. Go up those stairs there and through that window. If the fire had started over on the sofa where the investigator thought it started because the most severe damage was in that area, then how did we get the damage in the stud channel behind the stove and the joist channel above the stove? Well, the investigator said, well, all the hot gases just naturally flowed over there. The ceiling was covered with sheetrock. How did it get through the sheetrock and only attack one stud channel? It didn't do all of them, it was just the one. If the fire had burned over there, all the hot gases would still have gone up the stove. I mean, up the stairway. There's no reason for them to go to the other side. Here's a fire test that we did a few years ago, a model of a test we did at CCAI down here. Some of you may have seen this. It's a 2-room apartment that we built. The left side of this room, this apartment area, is a kitchen, that kind of a kitchen. The right is kind of a living room with an open door to the outside. There is no door from the kitchen to anywhere except into the living room. So here's our fancy living room. We were quite the styling kind of folks setting that up. We've got thermocouples set up in there. We've got some wood paneling on the wall, lots of polyurethane foam, curtains hanging, the whole bit. This is our kitchen. We have real kitchen cabinets up top, some appliances on a cabinet down below. And at the very far right in the center of this picture is where the fire started. We also have a leather-bound sofa to the left, and the walls are all covered with wood veneer paneling, very light paneling. So we start the fire here on this stove top or cabinet top to the right, okay, down below the upper cabinets, and allowed it to burn. Notice what happens down low when we have an elevated fire in that room. The smoke will never burn below the base of the fire. So as a result, we don't get a lot of heat down low in this room. As the smoke drops, it also is able to go into the other room. One of the things we haven't talked about today, because we didn't have a lot of time, is when you have a flame that's burning and the smoke comes down over the top of the flame, it chokes off the oxygen that is used to oxidize all those red molecules. And so you end up with a lot of carbon monoxide, partial burning. The partial burning is because we can't get good entrainment in there. There's nothing to provide fresh air. So the CO levels go through the roof, pardon the pun. Go very, very high. Remember, mom had a CO level of 60%. The kids and the dad had no indication of smoke problems, even though this was a 1,200-foot apartment. This is our living room. We know the fire didn't start there, but let's look at the living room in the area of most severe damage with the kitchen. If you were to go in there and strictly look at patterns in the big generic macro sense, which of those rooms looks like it probably had the fire start? And look at that right over the sofa. The sofa's collapsed in the middle. We got a big V pattern like thing up above it, or a big U pattern. Looks to me like when I started this business, I would have said the fire started right there. It moved into the kitchen at a higher level and then just kind of burned some of the upper cabinets because it was hot and collecting at the top. The reality is the fire started right here, the right side of the cabinet, went up, created a whole bunch of carbon monoxide. The carbon monoxide ignited moved out into the living room, which has plenty of oxygen, ignited the curtains, ignited the upholstered furniture, the air coming in from the door hammers that love seat across from the door, leaving a beautiful pattern on the back wall, which would throw most anybody off. If you model this fire like we did in, you can see the picture here. This came from a model setup right there. What it shows is the fire very quickly goes out in the left compartment. The reason being, we fill that compartment with fuel gas. We don't have a source of oxygen in that compartment. The wood veneer paneling, all of that stuff very easily pyrolized, filling up the compartment with red molecules. Not only was it full of those and there was no oxygen, but they ignite, sending a flame front into the other room to the right. That ignites that furniture, which now has plenty of oxygen to support combustion. And that's what we ended up with. So, the investigator, going back to the other case, with my fire originating in the corner and all the testing of the outlets and everything, I determined the fire was incendiary. It had to be incendiary, it wasn't the outlets, and I know it was in that corner. So what do you mean? Well, it was set by a human. So the investigation timeline, father was indicted and arrested for the arson murder of his wife in 2015. A Daubert hearing was held starting in February of 2018 and finished in July of 2018. What do you think a possible explanation is for mom ending up screaming, naked on the floor, a countertop ripped off the counter, a single joist channel and stud channel burned, and the only arcing in the entire apartment being directly behind the stove. Oh, and a stack of pictures of dear old dad under George Foreman's grill. What's another possibility that was going on after mom got choked that morning, just for fun? How about the possibility that mom is really pissed, mad, she's been choked, she's been humiliated. She chases dad off. He goes into the bedroom, slides his box springs across the door to keep her out. Nobody hears the box springs leaving again. Dad's in there with pajama bottoms. She is so mad, she takes a stack of pictures of dear old dad and starts cooking them. I don't know if she was doing it with a lighter or the George Foreman grill, or what do you do when your blood alcohol is 0.27? She could have been. Yeah, you're right. She could have been. Possibility. Now let's talk about the pattern on that refrigerator door. It looks like it moved from right to left. No doubt about it. Is that a movement pattern? Could be entrainment. It could be the fact that we have this monstrous fire over here with a lot of fuel gases at high temperature. We have a kitchen with not super high temperature that still has wooden panels that aren't burned. And we just so happen to have damage all the way down to floor level out here and not quite so high in here. The overstuffed chair right there next to the refrigerator might have caused a little bit of local burning. Yeah, the point is maybe the overstuffed chair ignited during the fire, seal fails in the refrigerator, the door opens. Cabinet comes off, her clothes are on fire. We know she's clothed. Any possibility she could have ripped those clothes off, struggling around, flailing, trying to get away from being burned, screaming like nobody's ever heard her scream before, knocks the cabinet top or the cooked countertop onto the floor. Well, we found out the countertop wasn't bolted in, naturally. It's sitting there. So it could have come off pretty easy. The result was the judge decided that while the investigator appeared to have gone through a complete investigation, he relied solely on the greatest damage as being the indication of arson. This fire, there's a lot of other provisions about elevated fires that we got into that didn't have time for today. Consider those. He considered the fact that the arcing took place directly behind the stove. He considered the fact that a fire on the stove could have accounted for the single joist channel and the single stud channel that was burned. And he considered the fact that if she had caught fire on her clothes, she would have put them down, possibly ripped them off, and in the process knocked things to the floor. Her dropping to the floor and not being burned is consistent with an elevated fire with low heat fluxes at the floor and with very high CO levels. So the point is, you got to be careful. The investigator, immediately eliminated the kitchen. Some of the data he used was faulty. I think it was because he was so convinced that the fire started in the other room that he just went that way and didn't look at those appliances really. The other thing that he didn't consider, think about the airflow. Is there any way that a fire starting out in that dining room area would have created airflow that would have preferentially gone into the kitchen before it went upstairs? Never even considered the upstairs. Yes, sir. No breakers were tripped. Nothing tripped, and the panel was in great shape. So the result was, dear old dad spent 3.5 years in jail, which was probably a good sentence for choking his wife out that morning. And he was a real doozy, but there's very strong indications, maybe not complete proof, but at least beyond he knocked out the argument on the other side that beyond a reasonable doubt the fire started in the dining room. And particularly when looking at the idea of a fire starting and creating the most severe damage simply because it was at the origin, that was refuted. Okay, well, thank you for my absolute technical slice of heaven here today. I appreciate it. If you have any questions, I've got some of this material available on flash drive if you ever want to even bother seeing it again. I'm not sure I do. So,
Steve,
thanks.
real quick, on behalf of CCAI, we want to thank you for sharing your expertise and
Thanks,
knowledge
Steve.
with all of us.
Thank you. Appreciate it. Sorry, everybody. I really do apologize for the glitches here. Okay, take care.